Good afternoon, everyone. I am super happy to be here in JSConf. I am Matheus Albuquerque, and for the next half an hour, we'll be talking about compilers, static analysis, user interfaces, and how that all can be together. I'm a staff software engineer at this company called Medallia. I am a Google developer expert in web technologies, and you can find me pretty much everywhere as Y Combinator. Before we get into the technicalities of this talk, I wanted to share with you a little bit of a preamble on as to why I even wanted to be talking about this. And that's a story that starts 10 years ago, and it has to do with friends and printers. And you got that correct. I don't know if you've heard of this, but there's this language called ZPL, which stands for Zebra Programming Language. And it kind of looks like this. It's a bunch of, you have more than 100 commands, and it's a bunch of instruction sets that you can use to program the printers of this specific company called Zebra. And the story starts with this because I had this friend of mine, he was called Marcelo, and he was a researcher around programming languages and stuff, and he eventually ended up working with ZPL. And he was not happy about that. So he wrote a language that he named Capybara, and that language was a DSL that basically was inspired by Haskell, Rust, and many other programming languages. And it was extensive, it was modular, it has a lot of concepts like immutability in mind. And that language would compile to ZPL. And I have to say, this really blew my mind at the time because I was amazed by how he turned something like what you saw on the left into something like really neat, really nice to read and write as the one you saw on the right. And I started myself trying to learn more about that. At the time, I was also doing a little bit of Apple technologies like iOS and stuff. And I even tried to write a proposal or an RFC to bring in the pipeline operator to Swift. That proposal eventually failed. But it was super interesting because I learned a lot about DSLs, ASTs, ABIs, and all the lingo in this word. And this kind of changed the way I saw a lot of things when I was back to the front-end development 2 years after, in 2017. That's when I read this piece by Tom Dale. It's called Compilers Are the New Frameworks. And I really like this part. He says, so here's my advice for anyone who wants to make a dent into the future of web development. Time to learn how compilers work. And a few months later, in 2017, Dominic Ganway, the creator of Inferno.js and now of Ripple, and also a previous core team member of React and Svelte, he said, I personally think that 2018 will be the year that JavaScript frameworks start to become JavaScript compilers. And I saw all sorts of references to this, like when Ryan Corniato, the author of Solid, back when he was working for Marko in 22, he said, the thing that has made reactive programming interesting again are compilers. And for me, all of those were so interesting because so far I would think about compilers in JavaScript as those languages that we've seen hundreds of them that are the languages that compile to JavaScript. But if we think about it more, they are everywhere. Compilers and static analysis. They're in liners, formatters, bundlers, transpilers, type checkers, minifiers, the CSS tooling we have, and whatnot. So for the next rest of the talk, I have two simple goals with you. I want to somehow open your mind or maybe even empower you with certain tools that have helped me tackle many different challenges as front-end developer. And the other part is I want to bridge a little bit of the gap that I think that exists between the CS concepts we see and the practical front-end development we work on a daily basis. For that, the first part of my talk is called Compilers for the Rest of Us. And I gathered 3 cases that I've used recently in my company and previous companies, static analysis technologies. And the first one is about modernizing legacy code bases. And that's also the one that repeated more throughout different years. So You've probably been in this place if you're a React developer, for example, but the same applies to other technologies where you're going from one version to another of the library. For example, when you were going from React 15 to 16 and there was prop types, and prop types was moved to a different package. So it used to be part of React, but it was moved to a package called prop types. The same thing recently with React 19, where a bunch of APIs were deprecated. And the common denominator that helped me was code mods. So code mods are these different plugins in a way that you can use with this tool by Meta called JS Code Shift. And JS Code Shift is a tool that basically runs a transformation script over JavaScript or TypeScript files. If you've never heard of JS Code Shift, a simple hello world of it would look something like this. So it takes a file and then it exposes a bunch of APIs to access the AST of that code. For example, here I got one API that's called find variable declarators, and I'm finding everything that's called full, and then I'm renaming them to bar, and then it returns a new version of your source code. But you don't have to write all of the transformers. For example, there's a bunch of officially supported React code mods that solve, for example, the problem of prop types, just as many other APIs that were deprecated across different versions of React. And that's not only a React thing. For example, in my company, in one of the projects, we use WebDriver IO for end-to-end testing. And in this legacy code base, we were far behind. We were running WebDriver IO v4, and they also have code mods to go to different versions and to help migrating all of your WebDriver code. Not to mention that there's a bunch of interesting case studies out there, including Code Mods, the company who is one of the main maintainers of JS Code Shift these days. They have case studies on call.con and even Netlify of migrating really, really large code bases. And it's all over open source projects too, like Nuxt or even PNPM. And there's a lot of tooling that can help you with that, because even though there's a bunch of code mods ready for you to use, you can always write your own to modify the AST in the way you figured that your refactoring needs. So at the time, I was using a lot of AST Explorer. They have first-class support for JS Code Shift. But more recently, the Code Mods company, they released this tool called Code Mod Studio that allows you to build the AST, write your own transformers, and even use AI agents, of course, for that. So it's also super interesting. Anyways, if you want to know more about that, I have a whole case study of optimizing performance at my company using a lot of static analysis. But the TLDR here is that with static analysis, we could have a gradual rollout of two entirely different versions of the same code base that were bundled with different versions of developer dependencies, of app dependencies itself, like different versions of React, and entire different strategies for bundling and serving, so that we could simply toggle, we would all commit to the same code base, but it would bundle two entire different versions of it, and you could toggle on and off a feature flag to decide which version of the app you wanted to use. Another example was when we needed to understand millions of lines of code. So have you ever heard about this thing called Hiram's Law? Yeah. So basically, it's named after a Google engineer called Hiram Wright, and it basically says, when you depend on an API, you also depend on its implementation details. And I think the best way to explain this is with XKCD piece. It's very funny because it starts with, it's a bunch of release notes. So it says, the CPU no longer overheats when you hold down the spacebar. So they fixed something in this project. And then a user says, this update broke my workflow. My control key is hard to reach. So I hold the space bar instead, and I configured Emacs to interpret a rapid temperature risk as control. And then they go ahead and say, this setup just works for me, so please just add an option to re-enable the space bar heating. And besides this being really funny, the moral of the story is that every change somehow breaks someone else's workflow. And you can notice that in React too. So probably some of you have seen this internal of React that's called secret internals do not use or you'll be fired. And there's a GitHub issues from 2021 ask it, is it safe to use this internal? And then Abramov, of course, had to say, no, it's not safe to use. But besides this, again, being super funny, it's actually a problem out there. And a lot of libraries actually relied on this and other internals. That's why, for example, some of them broke with React 19. And I'm talking big stuff like Relay or Headless UI. And it all happened to a point that they even had to document when migrating to React 19, pay attention that you could be using libraries that depend on React internals, and this can be a blocker. So that's a little bit of Hiram's law, and that's how it happens with React, for example. However, with me, this happens in a different flavor. So I mentioned I work at Medallia, and one of the things we do are surveys. So we have the survey builder where people can build surveys and et cetera. And another thing we do have is it's a part in the interface where they can add HTML code or JavaScript code or CSS to basically integrate with things and customize the visuals and whatnot. So people can get really creative when they can write arbitrary code, of course, as long as it's safe. And we start experiencing the Hiram's effect because people start assessing internals like specific IDs, specific class names, and specific DOM structure. So they started writing code that relied on an internal DOM structure. So we needed to quantify that, and we came up with a complex pipeline that would take hours to explain. But I do want to talk about the part where we started to understand the code that our users were writing. And it starts with Bubble and Chirayo. So we started by trying to understand the HTML code. And one quick example of pattern we noticed is people would create a span element. It would have a specific class name called validation, and it would have a specific text within it called required. And with Chirayo, we can spot this kind of thing. It's really easy. We just need to look for a specific selector, in this case, the span with the class name, and then we can iterate and find all the occurrences of that selector and see if the contents of it matches required. So the whole thing would be approximately 6 lines of code. And here, we found a pattern. And we can do many different things with those patterns. We can productize this, and if we understand, for example, people want more options to insert extra required validation messages. But one thing that's more powerful than that is understanding the JavaScript code. So also with Chirayo, we can find all the script tags that people are including in those HTML blocks, and we can iterate for them and analyze this code. So understanding JavaScript code. So there are many, many different use cases for this, but one that I really find interesting is jQuery. So I don't have to do raise your hands thing. You all know jQuery. Most of you have worked with jQuery. And also, you're probably aware of some of the implications using that. So there's, you could have performance implications, and also depending on which version of jQuery you're running, you could have some security implications. You could be running a version with open CVEs, and you can get a vulnerability ticket in your application, this kind of thing. What a lot of people don't realize, though, is how popular jQuery is to this date. So as of 22, it was still used by 77% of the top 10 million most popular websites out there. So, and of course, we were part of this. So our users were also using jQuery. So again, static analysis, this time with Bubble. We are very, very used to thinking about Bubble as just this thing in our build pipeline, in the build pipeline of our applications. But Bubble is super powerful. It has AST tools. You can traverse ASTs. It has a parser and stuff. And with Bubble, we wrote a few hundred lines of code that told us how people are using jQuery. That could be, for example, which jQuery methods were being called, if people were extending jQuery, if they were using custom jQuery plugins, how they were extending jQuery. And this empowers you to have really complex analysis. For example, you can see what are the most used jQuery APIs. And you can see, for example, if they are using a lot of jQuery.css calls, they are customizing the look and feel of the application, just not the right way, but then you can guide them how to do it the proper way. And you can go one step further and even compile jQuery. So as long as, this is one example of compiling AJAX calls or web requests using jQuery.ajax. to regular native fetch API calls. So you can, for example, provide your users with tools to migrate their legacy code to more modern standardized web APIs. Another thing we also did in the same context was actually, so we understood how people were using and writing code. We also wanted to generate code. So again, that very, very complex pipeline. Basically, we were fetching code using those Groovy scripts. Groovy is a language that runs on JVM. And basically, those scripts, they would give us plain JSON files. So it was not like GraphQL, gRPC, or any other backend that gives you, that is very easy to integrate and get types out of the box. So we had to build types from JSON samples. And there are many tools out there. You've probably seen some of them. We ended up going with this tool called QuickType. But one common denominator for all of these tools is that there's only as far as you can go with static analysis. So if you have a JSON that's complex enough, you will have some issues with the output of the tool. The type definitions created are not going to be perfect. So we wanted to improve the TypeScript definitions and files coming out of those JSON blocks. The way we did it was with tsmorph, which is a wrapper around the TypeScript compiler API. And just one example of kinds of things you can do with it. Think of any refactoring of TS code. So let's say you have some arbitrary code that is not following your standards, and you want to, for example, convert those unions and that interface to follow certain standards you have for enums. So you can do that in few lines of code. And I mean literally less than 20. By the way, you have the slides, so don't bother trying to read all the tiny fonts. But with less than 20 lines of code, you can iterate through all the type aliases of a certain TypeScript code and make it follow the patterns of your code base. Summarizing this initiative to quantify the Hieronymus law effects in our code base, basically with static analysis, we had metrics around user-generated content that were based on plugin composition, because we could write any sort of plugins that would consume Cheer.io or Babel or any other static analysis tools to generate reports on it. And this data was the single source of truth that guaranteed consistency across the backend endpoints of the Node application as well as the React application on the front end. And with that, we have very, very rapid iteration, because as you write more plugins, they get instantly typed. And those types are reflected from all the way from the backend to the front end. And because they're just plugins and they're composable, you can write different tools. For example, you could write another module that is using AST grep instead of Cheer.io or Babel, for example, to go through the code. And for me, this is really mind-blowing. Every time I have an opportunity to adopt and to work with one of these concepts in my daily life, it's always amazing. And the reason why I started to have the first half of the talk with those practical examples is because when you start very theoretical on these talks, it's easy to hear something like, yeah, you're not Facebook, you're not Netflix, you will not run into this sort of problem. So yeah, there are everyday solutions that we can build with this kind of thing. But I think it's also an interesting exercise to think, what if we were them? What if we were Meta or Vercel or Void Zero or any of these companies building frameworks and front-end technology? Well, in the morning, we had a great example with this amazing talk by Ivan Yu from Void Zero, talking also about static analysis and compilers. But I also wanted to share a bit on compilers and our tools. And again, we have so many great examples in the world of front end of tools, frameworks, and UI renderers using in different levels compilers and static analysis. I wish I had the full day, but we have a limited slot of time, so I wanted to talk a little bit about some of them. The first one is Million.js. So Million.js was introduced back in 2024, and I think it's very interesting because it's, in my opinion, really good usage of AI and other things that are not just AI for the sake of AI. And if you've never heard of Million, it's this extension that helps you identify and fix performance issues in React components. And it gives you all sorts of insights like, okay, you have a very slow Redux selector, so you maybe could optimize that with reselect, or you could use this other library called use context selector, or you could wrap your code with the transition, and so on. And what's interesting about Million is how it works under the hood. Because when it looks at regular React code, what the Million compiler does, the Million lint compiler does is it injects calls to this Million capture instrumentation. And what Million capture does is when your code runs, it will gather metrics about its execution, like the amount of re-renders, how many each of them happened, the duration of the issues you had, and all of that. And that's then fed into the LLM. And this LLM is fine-tuned to give you hints on performance optimizations. So you're giving good information to the LLM to help you. So for me, that's very, very interesting case study about that. A few years before, so in 2021, we started listening a lot more about the React compiler that used to be called React Forget. By the way, a few days ago, it turned into 1.0, so it's now stable. And the compiler has a lot of capabilities, and what I see a lot is it's very easy to think that it's just about creating equivalent calls of use memo, use callback, and etc. But if you check the compiler playground and you run it with some React components and you see all the different phases of transformation that it does to your code, you see that it's actually a lot more than just generating the equivalent calls of it. So I wanted to talk a bit about two concepts that are behind the React compiler. The first one is called alias analysis. And it's a common technique in compiler theory. That's why you have a Wikipedia post about it. And that's used to determine if the variables or memory locations are referring to the same underlying data. And with that information, a compiler can, for example, optimize your code by reordering instructions or eliminating redundant code or even avoiding some side effects. And one JavaScript example of what this line of work wants to understand is this. So let's say you have a function, it takes an array, and then you assign 10 to the position 0 of this array, and then you assign that to a constant and return this value. So this value here always equal to 10. So you don't have to answer, but this is the kind of questions that this area answers. And an application of that in a React component is, let's say you have a component, it takes two props, then you create an array called x, you push A to x, and then you alias x to y, and then you push B to y. So if I asked you to memorize this with current React APIs, we would probably come up with some code that looks like this. So you wrap the whole x computation with a use memo, and then you do something analogous to y. And then this looks okay in the beginning, but then we start debugging, and we realize that in this particular case, it's not enough to simply memorize the computation separately. So then we would refactor the code to move the entire thing under to the same use memo call, update the dependencies, and so on, and that would work. So this is one kind of example of things that the compiler figures out for you. Another one, it's called static single assignment form, or SSA form. Just like compiler theory stuff, there's also a Wikipedia page about it. And it basically, this optimization aims to address the overhead of allocating the closures and dependencies arrays. And it does so by having the compiler inline conditional checks for those dependencies, caching the values, and reusing the cached values if the dependencies are the same. You can find this not only in the source of the compiler, but in the source of the compiler runtime too. You will see if you check that it uses something called use this function. It's called C in the source code of React. You can check the QR code for the source code of React. And the reason why I think it's relevant to mention two of the many CS concepts behind the React compiler is because beyond being this memoization compiler, it's also supposed to be this tool that understands your data flow and the mutability throughout your app and can actually help you with diagnostics of things like when you break React rules. This is from the React docs, by the way. Also, checking the source of the compiler and other stuff will help you understand how far it goes and what are some optimizations that they cannot do, so they will just skip over if you do this or that. Another example also by Meta is prepack. Prepack is not as popular as the React compiler, and it's not, unfortunately, it's not even actively maintained anymore. But it's very, very interesting to check prepack because it's kind of like if you check their source code and their rationales and design choices, it's kind of like a free compiler 101 lesson because you'll have symbolic execution, constant folding, lambda lifting, and a bunch of other concepts and techniques coming from advanced programming languages theory in a tool. Not to mention that back in 2018, they were actually drafting what it's like to have a React compiler. So not that React Forget came out of prepack, but it was a parallel initiative. And many other examples, like Svelte itself, it's also super popular, and it's super popular for being this solution built around compile time reactivity. And again, if you check the source under compiler and phases, it's a really, really good way to see the many different ways that the compiler will change your code and things it will track, because it tracks variables and their scopes. It identifies dependencies and detects statements that could be React statements. It handles event handlers, and it also scopes your CSS to also and optimizes the performance and a bunch of other things. And if, again, you check the playground, it's super, super interesting to see what the compiler would do to your source code in Svelte, including, for example, this is the reason why there's an asterisk is because it's pre-Svelte 5. But one of the very interesting things you can see that the compiler does is this $$ invalidate. It's basically one of the secrets behind the reactivity model of Svelte, where basically each variable that has been reassigned or mutated and referenced in the Svelte template is then assigned, is wrapped with this $$ invalidate function, and it's inserted right after the assignment or mutation. And what it does by doing that is marking that thing as dirty and scheduling an update for that component. And even though this function doesn't exist with Svelte 5 and the whole runes model, it's also super interesting that you run the Svelte playground with Svelte 5 and you see what the compiler is building out of your Svelte components. Because you'll find something like this $template effect or $delegate, and a bunch of other utilities that are handling under the hood the reactive state of your app, the event listeners, and dynamic expressions, and the templates and all of that. But I feel like I'm talking about a lot of things you already know, like Svelte, the React compiler, and etc. So I wanted to go a little bit back in time and talk about this. For example, the OPA language. Who here has ever heard of OPA? Okay, no one. So that was back in 2011, and it's super interesting. It never got a lot of traction, but basically you would have programs written in Open, and that would be compiled to Node.js on the server and to regular JavaScript client code on the client. And the compiler would automate all the communication between the two of them. And again, this was back in 2011. And if you check their code snippets, it's super interesting how at the time they had this, this annotation client and server. And the reason why I wanted to bring this is because it's super interesting to see how this challenge of code extraction and collocating client and server code and figuring out the boundaries and et cetera is not something that new. We've been investigating this problem for quite a while now. Going even a little bit back in time, Jaxer. Jaxer is this thing from 2008. It was by Aptana. This is a post by John Razik, the creator of jQuery, talking about Jaxer, by the way. And this Jaxer also tried to solve the problem of code extraction and client and server code collocation, even though they were not really doing that based on static analysis and compilers. But what it did have is it allowed you to have those script tags with this extra attribute called run at, and you could specify run at server, run at both, or and this, you're probably now thinking about RSCs or the compiler programs we have these days. For example, in Next.js, we have use client, use server, and also use cache. And in Solid Start, we also have use server, the use server directive. And even in other ecosystems, for example, Lynx, that was announced publicly this year, it's the React Native competitor by ByteDance. They also use compiler programs to break code that runs in the main thread and code that runs in the background thread on mobile. So again, I really wish I could spend the whole day talking about how these different tools are somehow leveraging static analysis underneath. But to wrap up, a couple of closing thoughts on this whole thing. I think it's really important that we stop thinking in this cliche that compilers are something for systems programming and this kind of thing that's not for us. No, they are now deeply embedded in the way we build, the way we optimize and reason about user interfaces. From transforming JSX to full-on UI compilers, we depend on them more than we realize. And there's this old saying in CS that is everything is either a compiler, a database, or a combination of both. And I think it's really interesting that we start thinking and abstracting things in terms of this. There's a bunch of interesting posts out there. This one is by Glauber, the CEO or CTO of Tursa database. And it's called My Other Database is Also a Compiler. And you've probably been in places where you didn't want to build a compiler, but you built something complex enough that could be a compiler. So if in a lot of occasions things could be a compiler, I think we can be creative about it. We can, for example, tackle complex challenges like mitosis and the way they use a lot of static analysis to transform JSX components for frameworks like Angular, React, Quick, Vue, and whatnot, but also other stuff like we as front-end developers, we build design systems. This is one example by Wrangle where they use the static analysis to basically figure out a big problem that is adoption of a design system. So they build a lot of static analysis-based tooling to understand that. My last note on this is I really think that understanding compilers can make you a better JavaScript or front-end developer. And again, you don't have to write one, but just knowing or having a notion of how they work can help you better evaluate frameworks. It can help you, it can influence certain architecture decisions and so on. And I really love this post. It's called What Can We Learn from How Compilers Are Designed? Because if we think about it, a compiler is a pipeline of simple or relatively simple transformations from data from one form to another form. And I think, I found this in a forum the other day. It's super interesting. The author says, there's really no better education on complex data structures and data processing and data types itself than compiler design. With the possible exception of network programming, I'd say all software development can be seen as a sort of subset of compiler design. And you won't have the complete picture if you don't understand it. I wouldn't be that radical about it, but probably the key takeaway of the last half an hour is I hope some of this changes a little bit how you see front-end development and front-end challenges and think about static analysis and compiler tools when you have a challenge again. And the original title of the session is Compilers, User Interfaces, and the Rest of Us, but the key takeaway is compilers are for the rest of us, are for JavaScript and front-end developers. That's my main message for today. Thanks for listening to me. The slides are available on this QR code and also on the conference website, and I'm going to be here for the next couple of days. So If you want to talk or have questions or anything, reach out. Thank you.